or by the end of the session, hopefully you will be able to explain the differences between measures of frequency and measures of association, calculate the appropriate measures of disease frequency and association and interpret the findings, and distinguish and explain the concepts of incidence and prevalence as well as their relationship to each other, and calculate person time based on a given set of data and use the data to calculate appropriate measures of disease frequency and association. I believe at the end of towards the end of the day you're going to be doing a practical which is based on this lecture, but you will require the basic understanding of these concepts throughout the next few days, throughout this week. I also want to highlight that these slides are at the courtesy of a lecturer at Imperial College London who taught me the same concepts, Philippos Philippidis. Okay, let's begin with the measures of frequency and very basic tasks of epidemiology. We basically want to, in general in epidemiology, describe the patterns of disease occurrence. So we have a health-related variable in a population of interest at a given point in time. Moima has already familiarized you with this concept, as well as causal inference, which is identifying determinants of disease and estimating causal effects of an exposure to a disease. The meaning of exposure I will go into more detail further on. I would like to remind you of some very basic descriptive statistics that are commonly used in in epidemiology at large, which are continuous variables. We normally use summary measures such as mean, median, and percentiles, and discrete variables including frequency measures such as proportion, rates, and odds. Whatever descriptive measure you choose in your analysis is dependent on the available data and the study design that basically determine which measures to use or not use. Again, very simple. On the top of a fraction, we have the numerator. At the bottom of a fraction, we have the denominator, which will be key to understanding ratios, proportions, and rates. A ratio is obtained by dividing one quantity by another in general. And those two quantities, so numerator and denominator, don't have to be related. It can include rates and proportions. As an example, you could have the number, you want to calculate the number of stillbirths per 100,000 live births. In that case, you would take the number of stillbirths divided by the number of live births times 100,000. Proportions are a type of ratio in which the numerator is included in the denominator. So let's say, for example, you want to estimate the proportion of smokers among adults. You would take the number of smokers in the adult population. You want to take the number of smokers in the adult population and divide this by the number of adults. Your result from this will always be a number between 0 and 1 and is often expressed as a percentage. A rate is a measure of how quickly something happens, and that's very important to note. It is always a time-specific measure. For example, you could calculate the number of new cases of cancer per 1,000 person-years of follow-up. Then you would take the number of new cancer cases and divide it by the number of person-years of follow-up times 1,000. And the denominator is always a measure of person time. So person time could be hours, it could be years, it could be minutes, depending on what condition you're looking at. Let's look at a real-life example. It's called classroom sleeping disease. In short, CSD. It's a widespread condition in schools and universities and disproportionately affects children, adolescents, and young adults, as well as students in the 11th floor of Nairobi Tower, University of Nairobi Tower. There is a growing interest within the academic community. As you can see here, we have about 110 million results to the question how to avoid sleeping in class. Common risk factors leading to CSD are alcohol consumption before, Sunday blues and sleep deprivation. But that can lead to long-term consequences such as low grades, exam failure, and musculoskeletal pain. So this is all fictitious, yeah, just to remind you. But as a good example, at the moment, 11 a.m. in this epidemiology class, everyone is awake. But at 12 p.m., so we're looking forward, 6 people are sleeping. So we could calculate the odds from this. The odds is the ratio of the probability of an event to its complement. So the ratio of the number of people who have the disease to the number of people who don't have the disease. So in our previous picture here, we actually have 18 people that are still awake. In my lecture, I'm very happy about that, but 6 fell asleep. So the odds at 12 o'clock are 6 over 18, which is 0.33. Prevalence is a snapshot of the current situation, and it measures the extent of existing cases of a health condition of interest. You have 2 types, whereas the point prevalence is the more commonly used one, but you can also, you might also find in the literature the period prevalence. The point prevalence is the proportion of individuals in a population who have the disease or the attribute of interest, whatever it is, at a specific time point. So you would take C over N, where C is the number of existing cases over your total population at a given time point. It is very important in this case to always define the time point, because if you look at the point prevalence of today, it may look very different to the point prevalence of last year on the same day, because conditions change. So you always want to include at the given time point you're looking at. Going back to our classroom, we have still 6 people sleeping at 12 p.m. And so we would be able to calculate the point prevalence from this basic information where we have 6 people. But rather than 18 in our odds calculation, we take the entire population, which is 24. So that is 0.25 or 25% at 10 a.m. This is dimensionless, but as you see here, I'm stating, sorry, it's not 10 a.m., I'm wrong, 12 p.m. Okay? This is meant to be 12 p.m. The period prevalence, which is less commonly used, is the proportion of individuals with a disease or condition at any time during the time period of interest. So that includes cases arising before and during the time period of interest or study, provided that they were present at any point during that time period. So for example, if we look at master's students over the past year, say 34% at some point were had the common cold. So that doesn't mean that at the end of this period 34% are sick, but at some point at the throughout the 1-year period they developed the common cold. We can use prevalence to obviously assess the health status of a population, but also to plan health services and allocate resources, to monitor time trends in chronic diseases and other cases as you may see fit in health policy development. But it may not be useful for causal inference and diseases with a very short duration. What impacts prevalence? Basically, it reflects both the occurrence and the duration of the disease. So prevalence would decrease if the occurrence of the disease decreases, or if the cases are cured, or if the cases die earlier. So this is a question now for you. How would you interpret higher diabetes prevalence among non-smokers than smokers? I wish I had a prize. So the answer is on the slide. It's in the 3 sub-bullet points, but which one would it be? Yeah. Yeah, go ahead.
So my thoughts would be the smokers are going to be dying
Yeah.
Risk factors of smoking. And then now we have non-smokers being majority of them. Still have mortgages.
Right. Those are our survivors. Exactly. Correct. Fantastic. Cumulative incidence is the proportion of the population with a new event occurring during a given period of time. It measures the occurrence of a disease within the population, but importantly here, it's the number of new cases during a period of time over the number of disease-free individuals at the start of the time period. Remember this definition. I will ask you something in a minute. During a given time period, again, we need to define the time period ahead. I wrote my exam in epidemiology, and we were brainwashed to always put the during a given time period and always specify the time period, otherwise we would be discounted hugely. I don't know if there's an exam for this classroom, but if so, keep that in mind. Naturally, looking at a long enough time frame, at some point you would expect the cumulative incidence to reach 100%. So, looking at this classroom CSD image again, I wonder if you could come up calculating the cumulative incidence. I will bring up the formula again. Okay. Who would like to try? I know I've got epidemiologists here, so please. Yeah.
Just to clarify, so the total size of the class is 6?
Correct. Yeah, sorry, I should have explained. So here we're looking at 11 a.m., 12 p.m., 1 p.m., 2 p.m. And we're looking over we're looking at the cumulative incidence. Yeah.
So at 11, obviously we don't have any. So at 12.
Yeah.
So that would be the number of cases. So the number of people who are sleeping, which are 2, divided by the number of people who are not sleeping by that time, which is 4.
I will let someone else try again. Okay. Yeah?
Okay. For 12 p.m., the number of new cases is 2 people are sleeping.
Yeah.
And then the number of cases is still 2 people are infected, minus the 4 individuals at class 4.
I will let someone else try again. Third try, and otherwise I will explain it. So the formula, yeah. Yeah, go ahead.
So at now the diagram, the image you're showing. So at 12, those people who are sleeping, are they sleeping at the beginning of 12, or at what time of 12?
Let's say they have CSD. They come in and sleep. They have a problem.
So exactly at 12 they're sleeping.
Yeah, they're sleeping.
Okay.
So maybe you go to the diagram.
Back to the diagram. Okay.
So,
Yeah.
so my question is, what's the formula, the the number of disease-free individuals
Uh-huh.
from the beginning of the time period.
Yeah, yeah.
So I'll assume our time period is at 11 a.m. and all of the 6 were disease-free.
Yeah.
So do we calculate cumulative up to 2 p.m. against 11 a.m.?
Good question, and that is like getting us to the answer.
Yeah.
Our denominator is defined by the start of the classroom. How many disease-free individuals are there?
6.
6.
Yeah.
How many CSD cases do we have? Eh? No. Like, sorry, I will explain it. So at 11 a.m., no one has the disease. 12 p.m., 2 people are sleeping. 1 p.m., 3 people are sleeping. 2 p.m., 4 people are sleeping. Okay. What, 9? Where are you getting to 9? So here we're looking at time. We're not adding up. These people stay asleep. Okay? You will get another one. You will get another one. Okay. And what is important about this? Someone points it out now. What is important about this? What did I not say now? We said 4/6 and over a 3-hour period. Important to note, yeah? So if you say that, if you say that over a 12-hour period, everyone is asleep after 12 hours. What is the cumulative incidence of this?
I think the first one is still not coming out clearly.
Okay, fine. Sorry. Okay. We have, this is our disease-free population. There's no CSD.
Yes.
Our classroom, we only have 6 people.
Yes.
Here, over time, we have 4 people who developed CSD. 4 over 6. Over 6, yeah, that's right. We're looking at a period of 3 hours. Over a 3-hour period. Jeanette,
Yeah, so I see where they're getting a little bit
lost.
yeah. So everybody thought that
This is the entire classroom. No.
That this person, let's say this person,
Hmm?
should also be a male here.
Oh, shame,
Yeah.
sorry.
So everybody is this a new person? Is this
Oh,
what's
no.
going on? But let's say Paula just, okay, so.
No, it's a closed cohort. It's a closed cohort.
Yeah,
so
so
they,
there should be like 3 men and 3 women.
right.
So when it changed, people got.
That's very awkward.
Yeah, but
Yeah.
I think what you're saying is once somebody's asleep, they stay asleep.
Right. Yes.
And at the end of it, it's like once somebody has hypertension or HIV or what, like once they have it, they have it. So it's not like you can have it, then you come out of it, and you go in.
That's right. Okay. So no transgender happening here. Yeah.
So in some clauses, let's say, are we summing up from, are we assuming
Yeah.
that the total population is from 11 a.m. to 2 p.m. or we are just concentrating on 12 p.m.?
No. From 11 a.m. We're looking at 11 a.m. At the beginning, we have no one with the disease, and it develops over time
To 2 p.m.
to 2 p.m.
So the total population at the end of the day will be 2 p.m. That includes the ones that are sleeping and the ones that are not sleeping.
Yeah, the size of the population never changes. It's a closed cohort. We assume that no one leaves the room.
So that means, based on your formula, we're assuming that at 12 p.m. we have 2 incidents,
Yeah.
the 2 sleeping. So the total will be, let's say, 1, 2, 3, 4, 10.
What is your total population for
I'm
you?
assuming from 11 to 2.
What is it, the number of people? How many people are in this population?
We have 6. I think for me it's 24.
No.
So forget the changes in male, female. Let's assume they're all the same. Yeah.
So
Yes, that's right. That's why we have the times here. Whereas the previous, where I was on the side, where my icon was on the side, right? Here, this was a class of 26. Yeah, but here we're looking at how it changes over time. Okay? Cool. Now, don't call me out on the gender problem again. Sorry. This is what it would look like, and it's important to state the time period. Now do it again. What is the cumulative incidence? Correct. 4 out of 5. Whoever said that is correct. 4 out of, no, but not quite. Over a 3-hour period. Okay? Because if we have a case at the beginning already, that is not part of our total population. We're only looking at the disease-free state. Okay? Cool. There are a lot of other names for cumulative incidence. Incidence proportion, risk or average risk, attack rate, so that's the proportion of individuals that develops an infectious disease during an outbreak. I mentioned earlier a rate is always a time relative measure. An attack rate is not a true rate. It's very confusing. Similarly with the case fatality rate is the proportion of cases who die among those who develop a disease. It's a very common metric in infectious disease epidemiology, for example. Again, it's not a true rate. Okay. Now, as we figured out, there are some problems with cumulative incidence. It requires a follow-up study. So you begin with the first one, with the first cohort at 11 a.m., and then you need to do the same thing with the 2 p.m. cohort. But this is a fixed period of follow-up, and it cannot be estimated from surveys or cross-sectional studies. So you need to follow the entire cohort over time, and it has to be a closed cohort. So you call this the studies in which you would be able to calculate this from is also called cohort studies, where basically no one exits the room. So there's no new member coming into the room and no one exiting the room unless they die. The survival proportion is basically the complementary to the cumulative incidence, where we take 1 minus the cumulative incidence. It's defined as the proportion of people in a population who do not become cases during the period of interest. So if you take the cumulative incidence plus the survival proportion, that would always be 1. What is the survival proportion in our classroom here? 1 over 5? You're right. You're right, and the slide that I'm showing next is wrong. I did the same mistake as you guys, sorry. So this is wrong. I will correct it. 1 over 5. Is it 1 over 5?
Yes.
We have 1, 2, 3, 4, 5. But this one is not disease-free. Yeah, so our cumulative incidence was what? Our cumulative incidence? No, but this person is the same as the other one. That person has been asleep all the way. 3 over 5. 1 minus 3 over 5. 2 over 5. Over a 3-hour period. Okay, wait, we do it again. This basically is excluded from our cohort because this person is already sick. So our disease-free population is 1, 2, 3, 4, 5. How many cases do we have here? No. 1, 2, 3. Right. What is the survival proportion? These two guys didn't fall asleep. Yeah, so it is 2/5. Okay? So which is the same as 1 minus 3/5. You got it? Cool. So I did it wrong. I counted 6, and that was wrong. Problems with cumulative incidence is that you may experience a loss to follow up, so not all subjects are followed for the entire time period. You have competing interests, so events that remove a subject from being at risk for the outcome of interest. Say, for example, they have a coffee, and then they wake again. Or cumulative incidence may not be well defined in a study. And the problem is also you cannot apply it to open cohorts. So subjects in which, cohorts in which you have people entering and leaving the population at any time. Then this doesn't work. We can mitigate this issue by using person time, which is the sum of the time period spent in the cohort by each individual. So let's say you guys are all spending 3 hours in this room, but one of you guys have to leave to go for a meeting, then maybe they only be spending 2 hours in the classroom. So their person time would be 2 hours. Because for that, we only need to look at the individual. We don't have to assume that it is a closed cohort in which everyone stays in the cohort. We only need to look at the time period that they stay here. Persons can contribute person time during the time they could have basically developed the disease. So say at any time in the classroom you are able to develop CSD, the sleeping disorder, yeah? Until diagnosis, death, or loss to follow up. And as I mentioned before already, depending on the interest or on your study, you might use person years, person day, person hour, person minute, whatever time measure you want to use. What is the person time of this cohort here? Here we have 11 to 12, no gender changes. And what is the person time here? 1 hour. The person time here, 2 hours. Here, 0, because the person was already asleep at the beginning. So this is not relevant person time. So we have 3 hours of person time. And we can use this to calculate the incidence rate, which is the number of new cases per unit of person time, PT, during the follow-up. So it's the number of new cases over the total person time, but that will basically give you the incidence rate, which is the average rate during the study period. So looking at this again, what is the incidence rate? I will go back to the formula. Any guesses? Yep. Jeanette is coming with a microphone. Yeah.
Please go back to the previous slide.
Yeah.
You know,
Oh, yeah, sorry, this is person time, PT. Question? Oh, yeah. I think I need a pointer, it would make. This one? No.
If I could add, like, if this wasn't sleeping sickness and it was HIV, you know, once somebody gets HIV, let's say at 1 p.m., at 2 p.m., it's not a new HIV, it's the same, yeah.
Mm-hmm. Yeah. Perfect. Fantastic. That's correct. I think you're missing something. Thanks. Or you could say per person hour, correct. Okay. Well done. The incidence rate helps us because it accounts for the time for follow-up. It is suitable for open cohorts. So say people come and join the class at some point, then we could still measure their person or account for their person time and risk of developing CSD or the disease. We can deal with competing risks as well as loss to follow-up. So by just taking only the person time that they spent in the classroom. And it can be expressed in different ways. So for example, 0.2 cases per person hour, or 20 cases per 100 person hours, so just inflating it to 100 person hours, or 4.8 cases per person day. Again, the units must always be defined. Now we're going to do some math. If we choose a very short follow-up time, let's say a few minutes, then there are no competing risks, right? And there is no loss to follow-up. So no one would leave the cohort. We remain a closed cohort. Then we can call this time interval delta t, so the triangle t. We can calculate the density of the cumulative incidence during this time period by the cumulative incidence over this duration, triangle t, delta t. Damn it. Sorry. This should be just C. So C is the number of new. N is our total population. And delta t is the period of time. Okay? So the cumulative incidence over that period of time is equal to the new cases over the person time, which is approximately the new cases over the person time, which is the incidence rate. This is in mathematical terms what we just concluded before on the previous slides. Okay? We will get back to why this is relevant in a bit. Now, the relationship between the measures of frequency. As I had mentioned before, the word rate is often somewhat, not inappropriately, but incorrectly used to describe cumulative incidence. So we see attack rate, death rate, case fatality rates. Proportion and odds. You may be familiar with the term prevalence and cumulative incidence. Those are both proportions, and they are fairly intuitive for humans to interpret. Say, for example, you run across the expressway, you have a 75% of chance of dying. Yeah. What is less intuitive is talking in odds. Unless you speak to an English gambler, you would say that you have 3 to 1 odds of dying when running across the expressway. Odds are often used for technical reasons, so that's a very common metric you would see in the literature nonetheless. How do proportions and odds map to each other? Basically, odds are the proportion over 1 minus the proportion. So they complement each other. Whereas proportions are the odds over 1 plus odds. Okay? What are the odds of developing CSD in this classroom at 12 p.m.? Yeah, I can see a hand. Yes. Go for it. Yes, you. Yeah, I don't know your name. Sorry.
Before I start, maybe I get clarification. So that's a total number of 26 people.
26.
24.
Ah.
24 people.
Yeah, yeah, yeah.
So the odds that you're saying is the proportion of those who have the disease, in this case would be 6 people, total of 6 people.
It's not a proportion, it's the number.
The number of people with the disease is
Yeah.
6.
Mm-hmm, mm-hmm.
And the number of people without the disease, therefore, would be 6 minus 24, which is 18. Yeah. So therefore, the odds will be 6 over 18.
Yeah. But so you could either do it in the absolute numbers, but if you followed this calculation, then you would take the proportion. So what is the proportion of? You would take the proportion of the total cohort, so 6 over 24. Yeah? Divided by 1 minus 6. Exactly. Okay? 1 minus 6 over 24. So that is the proportion. You actually arrive at the same result, but let's keep this formula going for now. And what are the odds? What is the proportion now? So what did we calculate as being the odds? Did someone say something? Hmm? 1 over 4. Yeah, it's correct, but how did you get there?
1 over 3 divided by 1 plus 1 over 3. Then
Yeah.
1 over 3, 1 is equal to 3 over 3. So that is 4 over 3. 1 over 3 over 4 over 3. Then it will be 1 over 3 times 3 over 4.
Good.
This is 1 over 4.
Good. Perfect. Did everyone get 1 over 3 or, no, sorry, 1 over 4 or 0.25 as the final result? Yeah, is it intuitive? No? Okay, let's do it again. What did you do?
I got confused at the wording.
Yeah?
Odds equals proportion over 1 minus proportion. So proportion to which they are percentage. So I did 6 over 24 times 100.
Y times 100?
6 over 24 times 100.
Where's 100 coming from? Proportion can be 0 to 1. So percentage is times 100. Fine. So let's say we stay with proportion. So then we have 6 over 24. And then? You've got it now? Okay. Okay. Yeah? Great. Okay, this is not in fractions, but basically in decimal figures. You will find that only for small proportions, the proportions and odds, the relationship actually becomes very close to each other. Okay? Looking at incidence rate and prevalence, prevalence basically depends on the duration and the incidence rate of the disease. If we assume that the population is in a steady state, so let's say we don't have any new birth and no death, or we have the equal number of birth and death, and the incidence rate and the duration are constant over time, then prevalence is equal to the incidence rate times duration. But that has limited practical utility. Some more math now. Basically, the cumulative incidence, which we can also call incidence proportion, can be calculated from the incidence rate, where we could say the cumulative incidence at a time point t is equal to 1 minus e to the power of minus the incidence rate times t. Now, this is not so intuitive, but a reasonable approximation is basically that the cumulative incidence rate at time t is approximately the incidence rate times t. So the incidence rate times duration. You will get those slides, I think, by the way, so you could look into it again. Okay, the association and causation. For measures of association, we always need to compare between groups. And in epidemiology, we would normally compare exposed versus unexposed, or those with treatment versus those having a placebo. And we use measures of association to quantify the strength of an association. We can do that on two scales: multiplicative, so that is a ratio, and additive, that is a difference. Those are widely used principles in epidemiology. When we look at causal inference, we have humans that tend to compare the outcome when action A is present versus versus the outcome when action A is absent, all else being equal. So if the two outcomes basically differ, with one being exposed and the other one being unexposed, then we can say that action A has a causal effect on the outcome. Say, for example, you have a new treatment option and you try the new treatment option and compare that to the status quo, so the do as per usual scenario, then, and you see a difference, then the action, so the treatment would have a causal effect of the outcome if it is different to the other group. We normally call A the exposure or treatment in epidemiology, where that could be behaviors, so smoking, drinking, diet, treatment, so having a surgery or not, genotype, occupation, environment, and there are a lot of other factors that may or may not lead to you having a disease. We also often speak of counterfactuals, which are the potential outcomes that would have been observed under each possible exposure or treatment value. So it's the counter to the fact, the counter to the status quo. For some subjects, they are the outcomes that would have been observed under an exposure or under treatment value that the subject did not actually experience. So it's the hypothetical. To talk about causation, we need to talk about counterfactuals. We always have to have something to compare to, basically. But they are not necessarily part of the statistical language. Whereas in statistics, we use the language of association, and you might be more familiar with that, having a background in statistics. But causal concepts cannot be represented using purely statistical language. Effect is, if you look at let's say at our classroom again, or we look at lung cancer as an effect of tobacco smoking, that is basically the end point of the causal mechanism. Okay? So for smoking, you would always have, well, in most cases, have the outcome of death as your effect. In association, we compare the measures of occurrence in two different populations or two subpopulations. So, for example, you could take the same population at two different time points, this classroom today versus this classroom exactly 1 year ago, or after an intervention. but you cannot normally compare populations. They are not like for like. The USA is different to Kenya, for example, and they're not exchangeable. So you could compare the cancer incidence rates between two countries, China and the US, or Kenya and the US, or between females and males, but you need to adjust for other characteristics in the population groups. Okay, and finally we have measures of association. These can be in absolute or relative measures. Absolute effects are basically, simply put, the differences in incidence rates, cumulative incidence, or prevalence. They are on an additive scale, whereas if you speak in relative terms, you're on a multiplicative scale, which involves ratios of those measures that are mentioned above. Looking at the risk difference, it's basically, so CI1 is the cumulative incidence of those exposed to the treatment or to the disease minus the cumulative incidence of those unexposed or not having the treatment, and that would be basically the cumulative incidence difference, so the risk difference. This table gives you the interpretation, is somewhat like a cheat sheet that you might want to use. Basically, if the risk difference is below 0, then the risk of disease among those that are exposed is smaller than the risk of disease among those that are unexposed, whereas it's the opposite when the risk difference is above 0. Then the risk of disease among those that are exposed is greater than the risk of those among those that are exposed than those unexposed. If you speak in terms of association, then the exposure is the decreased risk of disease, and if the risk difference is larger than 0, then the exposure is associated with increased risk. So for example, if we have a risk difference of 0.2 over 1 hour period, then in associational terms, we could say, for example, there was a 20% excess risk of sleeping in class over the 1 hour period in those exposed to the boring lecturer compared to those unexposed. An alternative way of saying this is that there were 20 more CSD cases per 100 people over the 1 hour study period. In causal interpretation, you would be able to say that if everyone had been exposed to the boring lecturer, there would be a 20% excess risk of developing the sleeping disorder in the class over the 1 hour period. Or you could say if everyone had been exposed, there would be 20 more CSD cases per 100 people over the 1 hour period. The risk ratio is basically, as I said, it's basically taking the ratio of cumulative incidence among those that are exposed, so CI1, over those that are unexposed. Again, you can use this table as a cheat sheet on how you would interpret a risk ratio of below 1, equal to 1, or higher than 1. So if we had a risk ratio of 1 over the 1 hour period, then the students exposed to the boring lecturer had 2 times the risk of the sleeping disorder compared to those that are unexposed over the 1 hour period. If we assumed the causal interpretation, we could say that if everybody had been exposed to the boring lecturer, the risk of developing CSD in the class over the 1 hour period would be twice the risk had nobody been exposed. The incidence rate difference is similar to the other absolute measure that we had, the cumulative incidence difference, where we take the incidence rate among those that are exposed minus the incidence rate among those that are unexposed. But here, important to look at is that we use the person time as in the numerator. The incidence rate ratio is again similar to the cumulative incidence ratio, where we have the incidence ratio among those that are exposed over the incidence ratio among those that are unexposed. So if the result was 2.5 over the study period, then we could say that the students that were exposed to the lecturer had 2.5 times the incidence rate of sleeping disorder compared to those unexposed, or 150% higher incidence rate of CSD compared to those unexposed. And finally, we're looking at the odds ratio, where we have the odds of developing the disease among the exposed over the odds of having developed the disease among those unexposed. That gives you the odds ratio, and in when the disease is rare, the odds ratio and the relative risk is approximately the same. Okay. So that's the end of the lecture. I am hoping that you can explain the difference between the measures of frequency and measures of association, that you can calculate the measures of disease frequency and association. You can somewhat distinguish and explain the concepts, at least using some of these lecture notes, and calculate the person time based on a given data set. I think you will practice this, and the more practice you have in using these formula, the easier they get, or the more intuitive they get. But I hope this was an easy to follow reminder of the basic concepts of epidemiology. Finally, there is a hackathon that we are organizing that is taking place in January, for which the applications are currently open. If you want to find out more, you can scan the QR code. You can also apply via the link here and ask me anything about it too. That's in collaboration with SEMA and Imperial College. Thank you very much. Do you have any questions? Yeah.
Just wanted to get clarification. There's a slide about rankings, the characteristic and association. I didn't quite get explain more.
Okay. Say you're exposing yourself to smoking, nicotine. Likely, so your effect of smoking would be at the end of a time period potentially be lung cancer. Yeah, lung cancer could develop among anyone, but let's say you compare a study cohort of people who already have other conditions, or let's say you compare a study cohort of young people, 10 to 20 years old, that's bad, 20 to 30 years old who are smoking, and you compare that with people who are 40 to 50 years old. Yeah? So that is, you could potentially lead, that comparison could lead to an association. You're comparing the endpoints, so the effects of smoking in those two subpopulations. They are not, one term doesn't exclude the other. You're using those together. So you're measuring the effect in one population versus another one. But in this instance, if you compare the population of 20 to 30 years old to 40 to 50 years old, it's very likely that the outcomes are different because older people are more affected potentially by lung conditions, by respiratory diseases. Yeah. Yeah, go ahead.
So my question is, you showed example on a closed population. How will the proportion look maybe in a
Not sure. So you have the reason why I showed a closed population was because cumulative incidence, for example, you can only calculate in a closed population where no one leaves the room, no one changes their behavior, basically, no one has any intervention to them. Coffee would be an intervention in the sleeping disorder, or does that, so you cannot assume to use the same metrics for the same types of cohorts. If you know that it is an open cohort where people leave the room all the time and come back, then you would rather want to use person time, the time spent in the classroom under the same conditions as everyone else, somewhat.
And let's say there is change in proportion, like how the difference is in the stochastic and determinism. So if there is change in proportion
Okay?
from time period to time period,
Yeah?
how do we expect maybe let's say the proportion of the CI to
Jeanette, help me out here.
You said your background is modeling. You know, you said your background is modeling. Was it? Not really. Okay. It is. Okay, okay. So just to try and understand the question, I also don't think I fully understood. Where did you get it? Oh, George. Oh, okay. George.
So technically, when you're doing the person time, so you don't kind of, so normally you define time. So let's use the example that we're using. If we are following a study, if we are doing a study and we're following for 1 year, then we will be having person times depending on the number of people we recruit to the project. Now, I think the way you're thinking of it, let's take our mind off the stochastic vis-a-vis.
In terms of like things like censoring, dropout, and stuff like that. But then what you're going to be doing is looking at not kind of like a month-to-month change. It will be for the person time, the cumulative person time that you're working on. So I would like to take your mind a little bit off the model part and just kind of do this because we are building on something as we move through the week into it here.